Thank you very much. It's an immense honor to be here and celebrate two legendary mathematicians, the two legendary mathematicians that are awarded the Abel Prize this year. I actually don't feel like up to the task. I feel a bit nervous, like a kid who's actually in front of his superheroes. But nonetheless, the talk is not about me, but it's about the work of John Forbes Nash Jr. Okay, so as you have seen, the title is borrowed actually from the title of a famous book by Richard Feynman. So it has already been highlighted yesterday and today that John Forbes Nash is the solver of some of the most outstanding puzzles in contemporary mathematics. But there's one thing which is related to this in some way, but it's not apparent only from the statement, and it's something which is apparent from the people who have read these papers. And there is a sense of wonder when you read these papers, and sometimes you're actually wondering whether what you're reading really is true at the beginning. So it seems actually as if he's joking with you from his papers directly. But in fact, you later discover that, yes, it is true, and you have to change the way you actually thought about entire subjects. Okay, so let me first summarize the main steps of my talk. So we're going to have a short journey through the work of Nash, and so let me stress that this is just a personal choice. So I will start with the famous game theory and Nash Equilibria, which is the reason why he was awarded the Nobel Prize. Then, although I was strongly advised by the committee not to do that, I will present also briefly his work on real algebraic geometry, and then I will pass to the 19th Hilbert problem, and so to his works on partial differential equations, for which he has been awarded the Abel Prize. And after that, I will present the problem of embedding Riemannian manifolds, to which he gave enormous contributions. And in particular, I will focus more on the dark side, if you want, of this problem, which I will call the Nash-Kuiper phenomenon. And then I will end with a modest example of his legacy. So it's going to be a presentation in 6 steps. Okay, so let me start. So maybe first a disclaimer. So I'm not an expert of these two topics, so I might say a lot of stupid things. In principle, I am an expert of these topics over here, and I might equally well say very stupid things about them. So let me start with game theory. So let me start with an example which is out of textbooks. So you have, say, n firms which are producing the same type of goods, okay? And of course, they can decide, say, they're, for instance, Italian shoes. Okay, so they can decide, of course, on the quality of the thing that they are producing. And of course, if you produce something which has very high quality, then you have a chance to sell it at a very high price, okay? So if you call the cost co-i and the price pri, then let's agree that somehow these two numbers gives you actually the action that each firm pi is taking. Okay, after all the firms has taken this decision, then of course the consumers go to the shop and they have to decide how many goods to buy and whether they're buying goods from one firm or from one other firm. Okay, so let's say that actually instead of buying things in a shop, they can actually order on the internet, right? Which today is a much more likely event. And of course, so they're going to order NI products, and it's depending in principle from the actions actually that these firms are taking. As you see, it's very idealized. I'm not considering, for instance, marketing, which is an important portion nowadays. And then, of course, each of them is going to gain the difference in price and cost multiplied by the number of products that you're selling. Okay, so the question, or one of the goals of game theory would be, how do I model a rational choice, or how do I model rational firms which are trying to optimize in this competitive situation their outcome? So let me give you a couple of less serious examples. So say that you're a kicker and you're shooting penalties in soccer. So let's assume somehow that you're shooting them so fast that actually the goalkeeper has to decide whether to fall right or left just by chance, or he can actually stay, right? So you can kick left, you can kick right, but you can also speculate that actually the goalkeeper is anyway falling on one side and you can kick in the middle just high, right? It's very risky though. And then there is another very famous thing, which is the prisoner's dilemma. So that's also out of textbooks. So say you have two people, two rascals who are convicted for a minor thing, but actually the police suspects very much that they robbed the bank, for instance. And so each of them knows, it's interrogated separately, each of them know that they're going to jail for a certain amount of time. Actually, if they rat on their pal, they can be given a discount because they will testify against the other person, so they will be given a bonus. On the other hand, if both of them rat on each other, then they're not given any bonus and they're going in prison for the full time. Okay, so the basic issue is how do we model a rational choice here? Now, let's give a model of this in mathematical language. So you have n players, P1, Pn. They might be the firms, or they might be P1 and P2, so the shooting guy and the goalkeeper. And they take some actions, which are called AI. And depending on the actions that they all together take, each of them has a certain payoff. For instance, they receive a certain amount of money because they're selling a certain amount of goods. And of course, one important point is that the players in this game, they decide simultaneously, and they cannot cooperate. They cannot talk to each other. So how they're going to behave? Well, one thing that you have to put maybe in some situations is that this game is played all over again, right? So, for instance, goalkeepers are somehow playing a lot of matches. Of course, shooters are shooting a lot of penalties. Firms are producing goods all over the years. So this game is repeated all the times. Maybe you shouldn't go in jail too many times, so that's of course not a good example in this case. You're probably not going to play that game more than 3 or 4 times. Anyway, what surely happens is that if you take a very fixed strategy, so if you're, for instance, a shooter and you're always shooting on the left, the goalkeeper somehow has seen the tapes and he knows that you're going to shoot on the left and then he's going to fall on the left, okay? So that means that somehow you would like to put a certain randomness in your behavior, right? So in such a way that actually your competitor cannot predict what you're going to do. If you put a certain randomness, it means that you can invent a probabilistic strategy, which means that you will take each action, aj, with a certain probability pij, which pertains to you. Okay, now you have a cumulative probabilistic strategy. Of course, you cannot compute the payoff that you get deterministically, but of course you can compute the expected value. So what will be in average your gain? Okay, so a fundamental concept which was actually introduced by John Nash in his PhD thesis in 1950 is that of Nash Equilibrium. So if you have a set of probabilistic strategies, then this set is said to be in Nash Equilibrium if none of the players can find a better strategy that gives him a better average payoff if the others, they are keeping the very same strategy. And as it is well known, so in his PhD thesis, a fundamental theorem that Professor Nash proved is that for each finite game, so for each game as I described, there is at least a set of probabilistic strategies that is in Nash Equilibrium. Okay, now as I told you, this is not really my area, but it's easy to go around and find remarkable quotations about this work. So for instance, this is the quotation from another Nobel Prize winner in economy, Roger Myerson, and he says that the Nash equilibrium is the analytical structure for studying all situations of conflict and cooperation. Okay, so we are at step 1 of the journey, and we have seen already an impressive contribution actually from this outstanding mathematician in his PhD thesis. Let us move now to a second topic, which is completely different. So this is real algebraic geometry. You could think that it's a kind of aristocracy of mathematics in a certain sense. So it's obviously, I couldn't resist to, to highlight the impact of somebody who's giving a prize in PDEs, because PDEs is more like working class mathematics, which I come from. Okay, so what are you interested in general in several situations are, of course, systems of equations. So systems of equations in which the unknowns, right, x1, xn, they're just normal numbers. Now, one way actually mathematicians think about system of equations is that to consider all the possible solutions as a whole, as a set. So this means that, for instance, it might be described in geometric terms in some situations as a surface or a curve. Okay, so now it's very important. We are going to consider what mathematicians call manifolds. It means I will assume that the set of solution is described by a surface or a curve or a higher dimensional object which has no cusps and no crossings. I'm going to show you what that means. Now, maybe one is a very complicated system of equations. So I just made this up. I don't know if it has solutions, actually. So, but just to give you an example, what you could actually dream in this very general context. So the only thing I'm assuming is that somewhat these functions over here, these equations, they behave nicely if I vary the numbers, okay? But nothing more. Okay, so let me give you some examples of what it means nice. So you see this is the circle, right? So the solution to the equation x1 squared plus x2 squared is equal 1. Okay, this is already a more complicated object. It's called a spiral. And you see here it's two equations, and therefore it's natural to, in three unknowns, and therefore it's natural to expect that the solution set is a curve. Okay, let me show you something a bit more complicated. So this is a surface. The mathematicians will recognize that I kind of fakely modified a real algebraic surface in such a way that it looks transcendental. But anyway. And these are all allowed because you see they all are nice objects with no cusps, no crossings. But let me show you something which in our game for the moment is not allowed. So the solution set is not going to be nice if it has a crossing. So here you see a classical equation that has crossings. It's called emniscata. And here you see a solution set that has a cusp, right? So here you see that it's kind of ending up with a tip. Okay, so that's not allowed. Okay, now there is a very lucky situation when you're studying equations, and this very lucky situation is exactly the entire subject of algebraic geometry. It's the situation in which your solution set is described by polynomial. It doesn't mean it's easy, huh? It might be very difficult to actually describe a solution set of a polynomial, but it certainly is a much more comfortable situation than if you have a very complicated function inside, with like, I don't know, tangents, exponentials, and so on. Okay, so in 1952, Professor Nash proved a very surprising theorem, which was, I mean, in the form I'm stating it here, was slightly modified later by an Italian mathematician, Tognoli, in 1973. So this theorem says that if you have a nice solution set, even of very complicated, with very complicated equations, with some minor assumptions, you can actually modify to a nearby solution set of polynomial equations. So in some sense, the general kind of rough behavior of a surface, of a solution to a set of equations is like the rough behavior of the solutions to polynomial equations, which of course are in principle much easier objects. Okay, so now for the mathematician in the audience, actually, what is really a Tognoli contribution? So Tognoli refines the original theorem of Nash. He's taken up on his methods, which are revolutionary. And okay, so if you're a mathematician, the precise contribution of Tognoli is that in Nash theorem, the submanifold is actually diffeomorphic to a smooth connected component of a real algebraic variety. And the contribution of Tognoli is to remove disconnected here. Okay, so I'm not an expert of this subject, but I did the following. So I mean, there are books which are written out of this 20 pages paper. There's maybe a little bit less than 20, I think. So, and you just go to the analytical index, and you discover that this paper alone has generated a huge amount of concepts. So here we go. I took just a random book in real algebraic geometry. I went to the analytical index, and that's what I found. I mean, all those concepts are actually references to something which was present in the paper of Nash. And I think that gives you a powerful idea to anybody who's not an expert in the field, anyhow, on how influential this single paper has been, which is very remarkable in mathematics. I mean, normally you need actually more publications to make such a big impact. Okay, so let's move to a realm with which I'm much more familiar. So let me talk about the 19th Hilbert problem. Which was a very famous, one of the very famous collection of problems that was proposed by Hilbert at the beginning of the 20th century. Okay, so it's about the calculus of variation. So what is that? So let me give you a very simple example, which anyway will be the topic of, will be the main topic of the wonderful lecture that Professor Morgan actually will give this afternoon. Okay, so it's the so-called Plateau problem. So say you have a curve in 3 dimensions, and you are looking at all surfaces which bound this curve. Okay, so one thing you might ask is whether there is a surface that among all the ones which are spanning this curve minimizes the area. And of course, besides asking whether it exists, you could ask what kind of properties it has and so on. Okay, so this is called Plateau's problem. It's just an excuse to talk about the general problem in the calculus of variation. So you see, if your 2-dimensional surfaces in 3 dimensions were represented by the graph of a single function, you could actually explicitly compute the area in terms of the partial derivatives of the functions. And here's the formula, right? So this would be the formula if the surface is the graph of a function u. Okay, so there was a general problem by Hilbert posed in 1900, and the problem was, let us not restrict to something which takes the simple form, but let us look at a very general minimum problem. So it's a problem in which the minimum that you're seeking is in a family of very complicated objects. So the functions, so all possible functions are candidates in this minimum problem. And what you're trying to minimize is a typical energy, so to say. So for instance, in physics, often this would be related to the energy of the system. And it's some integral which depends on the function itself and on the first order partial derivatives on the function itself. So now the question is, if this little function f over here is a reasonable function, I mean, there are some assumptions to be taken, can you actually infer that there is a minimum which is a regular function, so for which you can actually compute the partial derivatives in the classical sense, maybe higher partial derivatives? Okay, so now this was still open I mean, this problem was still open in the 50s. I already hear some of the experts mumbling because so they will, I mean, the experts will say, oh no, that's wrong, actually there was an existence theory, it was possible to prove that there was a solution, the problem was actually the regularity. Meaning that mathematicians had a way to show that there was a solution which solves the problem, but they are not sure that it's sufficiently regular, that it's sufficiently nice. So that's why I put here the word nice. So the problem is really to show that there is a nice minimum, something which is a function that for which we can compute partial derivatives in the classical way, for instance. Okay, so the answer is yes, and it was given around the end of the 90s, of the 50s, sorry, independently by John Nash and my scientific grandfather, as it was already pointed out by Cédric De Giorgi. In fact, what happened is that De Giorgi and Nash, who were working completely separately and without having any contact with each other, they came out with an independent solution for the same problem, which, by the way, completed a very long program which was initiated before. So the completion of this program actually requires what is called the regularity result for linear elliptic equations with variable coefficients. So here you see the appearance of the reason why the 2 laureates have been given the Abel Prize, right? So partial differential equations. So what actually happens is the following. So if you assume to have a minimum for your problem, you can actually compute a first-order condition for this minimum, a so-called first variation, and you will find that the function has to satisfy a partial differential equation. That is, an equation which is bringing into a certain particular relations the partial derivatives of the function. Okay, so it was known that if you could prove a certain regularity theorem for solutions of such equations, you then would complete the program which was initiated by several other mathematicians and then answer affirmatively to the question of Hilbert. Okay, so this is all about it that I wanted to tell you. So let me also stress that the proofs are rather different. So nowadays this is called the Giorgi-Nash Theorem, but actually Nash's original paper deals with a larger class of equations which are called parabolic equations, for which the equations which are describing or first variation condition for the minimum in this problem are actually just a subset. Okay, so now let me get to the fun part of the talk. So, okay, so I'm going to explain you what is the the embedding of Riemannian, the problem of embedding Riemannian manifolds in the Euclidean space. I was told by the committee that this is a general audience talk. I shouldn't assume you know anything about submanifolds or manifolds and so on. So the mathematicians in the audience who might be bored by this, they have to blame the committee, not me. So let me start with this example. So say you are driving a very old car. So you are lost in the middle of somewhere. Some forest in Norway. I thought it's somehow a reasonable assumption for some of you. And the car is old, so it doesn't have any GPS. And what is very realistic, your mobile phone is dead, because after all, the battery nowadays, you know, maybe for a couple of hours survives. So now what do? How do you get out of the forest? Well, of course, what you hope is that you have a road atlas, right, in the car. I actually don't know how many people nowadays use road atlas. When I was a kid, I was fascinated by this. So my father always told me to plan the journey ahead when we would go on vacation. So I was always looking at the road atlas. So now, what is a road atlas for a mathematician? So how could you describe this? Well, you obviously have in your road atlas a collection of charts, right? So that's where you actually get the information, for instance, about where the road is going and how long it is. Okay, you have a collection of charts, and what is very important for us, that's because of, maybe you're not interested in that if you are in the middle of the forest, but for our game it's going to be interesting. It's the length of the curves, of the roads which you have over there, right? So you see all these, I don't know, blue, red, yellow curves on your map, and actually there are some numbers, which my wife always said it's difficult to decipher. And they tell you that that road from this city to that city is long, 20 kilometers, okay? Now, there's another thing that I want to draw your attention on. I don't know if you ever thought about this. The fact that charts overlap, right? So say you're going from Oslo to Bergen, maybe Bergen is at the end of the chart. Okay, so you look at the next sheet. Well, the next sheet overlaps a little bit with the previous sheet, right? So there is a small overlapping. And something which is interesting for us mathematicians, you in your mind have a way of comparing how the two charts overlap, okay? Good. So now, what's a Riemannian manifold? Well, you can think about a Riemannian manifold as a sort of generalization of a road atlas, a mathematician road atlas. So it's a family of charts in which you can compute distances between 2 points represented on the charts. And of course, the charts might overlap, and you have a rule to computing how the length of the road is in one chart and the length of the road is in the other chart. They have to match, of course. So this is a metaphor. Actually, the mathematician's atlas is a bit more precise. And one important thing is that for us, the two-dimensional world is very boring, so your maps may not describe a two-dimensional road map, but maybe, I don't know, a strange planet in which you live in 3-4 dimensions, whatever, okay? So allow me to do this. Now, one very important thing that you already see on this very simple metaphor is that your charts are very distorted, right? So you are actually representing everything on a flat piece of paper, but in fact, the land is corrugated, right? So there are mountains, there are valleys, and so on. So your map is not really a very precise description of your landscape unless you really read the numbers which are written in there, right? So if you're going to measure actually the length of the curves in there, they're not really a scaled version of the length of the roads that they are describing, because there are these distortions, right? Although maybe the guy who, the publisher told you that it's a scale 1 to 20,000, but it's only an approximation. In fact, this is very apparent if you look at the global atlas of the Earth. The Earth is curved. And if you look at the global atlas, of course, the mankind has always tried to picture the Earth on a flat sheet. So now there's going to be the following phenomenon. I wanted to do this with Norway and Italy, but it doesn't work. But let me tell you, I'm doing it with Greenland and Brazil. Right? You look it up here, Greenland looks really big. It looks almost as big as Brazil, right? You would agree on that. It's maybe slightly smaller, maybe, but it definitely looks very big compared to Brazil. But now, when you go and compute the area of Greenland, you discover that, at least Wikipedia says, that it's 2 million kilometers square, And Brazil, it's actually 8 million kilometers square. So Brazil is 4 times as big as Greenland, right? So there is a big distortion on the map. Norway is bigger than Italy, but not as much as it looks on the map. Okay, so now, what is the isometric embedding problem? So the isometric embedding problem is a reverse process, which mathematicians often do. So let's say that you run with your fantasy and you produce a road atlas. And you put curves on it and put kind of random numbers. Can I actually find a planet which has that road atlas as a description? So that's the question. That is called an isometric embedding of a Riemannian manifold. So your the road atlas that you created without any reference to reality is called an abstract Riemannian manifold in the language of mathematicians. And the representation as a planet is called the isometric embedding of the manifold. Very good. So now, see, I told you have to do things at random, but not too much, right? So you have to respect some rules. So for instance, if 2 lines are parallel, if 2 roads are parallel, if you give 20 kilometers to one and 40 kilometers to the other, then I'm not going to find a reasonable kind of planet which is going to do that. So you have to respect some rules in this. So that means I'm not telling you all that is hidden in this abstract Riemannian manifold concept. There's much more into it. And then, as I told you, last but not least, maybe you allow charts of something which is more than 2 dimensions. So 3-dimensional charts. I don't know. Well, you might think about distances between stars, for instance, but even higher dimensional. And what is more important, you allow me to realize my planet in more than 3 space dimensions. Okay? So just take it as it is. Okay, let me give you an intuitive explanation of what is going on over here. Okay, so say, this is a piece of paper, right? So if I draw a road over here and I compute the length of this road by, using something which in English I don't know what it is, right? like a meter, goniometer, whatever. So then you might wonder actually how many different ways I have to represent this chart inside, right? So it's clear that if it's completely flat, it's representing. But it's also clear that if I do something like this, right? So the length of the curves will stay the same, although the planet looks slightly different. So there's not a one-to-one map. So you might have the same road atlas for 2 planets which actually look different, okay? So now it's important. Yesterday, Robert actually spoiled this for me. Anyway, not so many of you were at dinner yesterday. So this is, for instance, one planet that I can do with a flat road atlas, okay? What certainly it doesn't seem possible is to bend it in this direction, right? Because, yeah, I can do it, but it seems I am creating a nasty thing over here, something where if you were an inhabitant of the planet, you wouldn't want to be, okay? Remember about this? So this problem, the isometric embedding problem, is a very famous problem, and very little was known actually before Nash, although there were actually, very little comparatively to what he did. I'm neglecting a lot of mathematicians actually here. So what was striking after the work on Nash is that we learned actually that the answer is very subtle and it depends on how regular is the planet, how many singularity you allow on planet Earth to realize your road atlas. So let me give you 3 examples. For all of them, you have to look at me. Okay, so I'm going to use mathematician words to discover particular different situations. So see, here I'm having a kink, okay? So this is going to be called Lipschitz. It's, it is reasonably smooth object, but it might have a kink, okay? So now, if I don't allow kinks, then I will call the realization C1. So it means I have something in which the tangent space is varying nicely and continuously. Okay? Very good. And then there is C2. C2 is more difficult to explain. So in C2, instead of having only tangent planes, you have quadratic approximations for the surface everywhere. Okay? So this would be C2. Let me show you something which is C2 but not C1. Something like this would be Sorry, something like this would be C1, but not C2. It's difficult to realize, right? So because up to here is described very well by something flat, and then you have to take a quadratic polynomial which does something like this. So very good. So now the answer given by Nash was the following. So for C1 isometric embeddings, so you can always construct your planet under the minimal dimension that is required by the topology. I'm going to explain this later, don't worry. Now, the second answer is that if you want more regular embeddings, if you want C2, then actually they do exist, but you have to go high up in the dimensions to produce them. Okay, so this actually generated an extremely important mathematical tool later, which is nowadays called Nash-Moser hard implicit function theorem. I mean, hard has been given by the experts, so you actually forgive me if I'm not going to explain you that part. But let me explain you this part instead. So here's a question for you. When you put a paper in your pocket, of course you fold it, right? So you do something like this. And then you put it in your pocket. Now, can you do it without folding? And of course you could take my idea, you know, do a very little cylinder, you're not folding it, and you're putting it in your pocket. Something like this. But now I also ask you that it's not going to get out. So it really has to be completely in your pocket. And now it starts being bad, right? Because if you attempt to bend it in this direction, you will create a kink. So can you do it? I mean, this would be what I call Lipschitz. Can you do it C1? And it seems impossible. But in spite of the fact that it seems impossible, it was the genius of Nash to actually show that it's possible. And it's actually possible irrespective of how big your piece of paper is, right? If you have a very small paper, of course it's possible. Just put it inside, even just by moving the cylinder. But if I have something very long, I have to fold it. Okay, so once again, we see another name to associate it to him. So the contribution of Nicholas Kuiper is comparatively small, although in the form I'm telling you, I have to cite him. I mean, because it was additionally proved by Kuiper that you can do it in 3 dimensions. Okay, so how's that possible? So it's very difficult, it's very hard to believe what the Nash-Kuiper theorem is telling you. And that's because if you were asking a little bit more, so if you were asking a little bit more regularity, a concept which is called curvature would kick in and would tell you that it's not possible to put this paper in your pocket. And you could prove actually a theorem, which is a classical theorem, which tells you that this paper in your pocket game in a C2 way is just impossible. Okay? So let me give you, anyway, a small description on how you prove a Nash theorem. So first of all, you shrink the Riemannian manifold. So you kind of shrink your piece of paper, which you cannot do, of course. So that's why it sounds very difficult to do it with a paper. But say instead of a piece of paper, it's a fabric, okay? And you do like the mistake that sometimes do, I put the fabric in the washing machine at 90 degrees, and then it gets shrinked. Okay, so now it's shrinked, and you want it to actually bring back to its initial length, right? All over. So what you try to do is you try to add wrinkles. So of course, you could sort of pull it back by doing this. It's usually very unsuccessful to put it back to its initial dimension. And then, of course, you would occupy a lot of space. Instead of doing that, you can try to add tiny, 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 tiny small wrinkles. Okay, it's not very convincing, right? It took 60 years even just to get a picture of this using supercomputers. So this is taken by a group of French mathematicians. This is an embedding of the so-called flat torus. So here, you're actually folding the piece of paper, which I told you is flat, even in the direction which looked impossible. So you're doing this. You're doing this, and then you're wrapping it up on the other direction, but you're doing it in a smart way, in such a way that you're not creating kinks. Okay, so that's how the picture looks like. And actually here you have a 3D printed object of that, which later on, when we have the refreshment, you can maybe, well, I'm not sure if you can touch it because it belongs to these French guys. So let's say you can stare at it from nearby. Okay, so now what about the legacy? So I'm almost at the end of my topic, so there's only one step to go. I think the organizers should not be nervous because it seems I am on time. So you see, the legacy of his work is just enormous. It's just beyond counting, probably. So already Cedric has mentioned plenty. It was, I mean, it's really, I mean, I think it would be like, you know, it would take you days to go there and count all the mathematical papers, but all the papers in other sciences, which are in some way using his work. Let me anyway give you a very modest example, which is related to my research, and which I think it gives you an idea on how I mean, his genius has crossed actually the boundaries of several fields in a way which I think it's unexpected. Okay, and it will be exactly on this exotic part or esoteric part of his work, which is called, which I called Nash-Kuiper phenomenon. So remember this wrinkled torus, because at the end I'm going to tell you that this wrinkled torus looks like something, okay? And this wrinkled torus will be called Nash-Kuiper phenomenon. Okay, where was that? Before. No. Right, Nash-Kuiper theorem. Very good. So now, so far, you have not seen any partial differential equation, right? So now I have to punish you with that. Okay, so it was already mentioned by Cedric, who spoiled part of the talk. So the Euler equations are a very classical systems of partial differential equations, which were derived by Euler more than 250 years ago to describe ideal fluids. So what does it mean, ideal? So I'm assuming the fluid is incompressible. So if a certain portion of fluid is occupying one cube meter, you can squeeze it, but then it will get out on the other side. It's still occupying 1 cube meter. And its status is described by two unknowns, which are called the velocity and the pressure. The velocity are actually very natural to describe. So see, the velocity is a vector function which depends on the space x and t, and it gives you the velocity of the fluid particle, which at time t is occupying the position x. So it tells you where that fluid particle wants to go at that instant. Now it's more difficult to describe what the pressure is. So this is the hydrodynamic pressure. It's a scalar function. So its gradient is a force. And one way to think about that is that this force is the reaction to the fact that fluid particles want to move maybe in the same point, but they cannot, because there is incompressibility. So you cannot put a very large portion of fluid into a small portion. And then the fluid is going to react to this movement, and that's given by this force, which is called the pressure. Okay, so here it's the system of partial differential equations in all its glory. If you know calculus, you know what I'm speaking about. If you don't know calculus, I'm sorry. Well, for the physicist in the audience, this blue term, which is the nonlinearity in the equation, usually in physics books is written this way, as the so-called advective term. And there is a small computation which shows you that the way I've written is equivalent to the way you would find it written in normal physics books, right? So it's this small computation over here. Okay, so let me do a very simple calculus manipulation to this. So if you take the first equation and you scalar multiply by v, you derive an interesting identity. This interesting identity is nothing but rate of change of the kinetic energy of a particle which is sitting at the point x and t. The one thing which I forgot to tell you is the fluid is homogeneous. It has the same density everywhere. And we mathematicians, when we see something constant, we put it equal to 1. So you don't see it appearing over here, right? So there should be a density. Okay, now, if you integrate this quantity in space, you find the total kinetic energy of the fluid. You see that this blue part is in divergence form. If you integrate by parts that quantity, you hope it's equal to 0. You will need some assumptions to say this. So you will need either appropriate boundary conditions, or you will need some decay at infinity if the fluid is occupying the whole space that you can imagine. Okay, so this is for mathematicians, just technical. So remember, the total kinetic energy is constant, which is what you would expect, right? Because there is no force acting on the fluid. So why should the kinetic energy actually change? There is no friction between the particles. Okay, it was already said by Cedric. Actually, it was proved in a remarkable paper in 1993 that there are solutions which are not regular, so they're very chaotic, and they might be at rest at time t equals 0, which means the velocity is equal to 0 everywhere. So the total kinetic energy is 0, But then later on, the total kinetic energy is actually positive. So it starts moving, the fluid, although you not exerted any pressure. And although I told you that the energy should be conserved according to the computation. So what's the problem? In the computation, I'm assuming the fluid is regular, so it's not too chaotic. So that computation is actually not valid for this solution over here. So now, I know what you're talking about, what you're thinking about. I mean, this is a typical useless mathematician theorem, right? So I'm Italian, I'm cooking the pasta. I'm not switching the heat below the pot. I'm not doing anything. And for some strange reason, the water starts actually moving without me exerting any force on that. It's unrealistic. I mean, thousands of years that we're cooking pasta, maybe less, and we never saw that phenomenon happening. I don't know, actually. So usually it's Italian moms that cook pasta, so honestly, I'm not completely sure of that. But I don't think my mom ever told me, oh, look, the water is moving. Okay, so although it's a useless mathematician theorem, it was actually remarkable that a Norwegian theoretical physicist who got the Nobel Prize for chemistry back in 1949 in his only paper on what is called statistical hydrodynamics, in which he was trying to describe a way to understand turbulent flows, he said, and he predicted, that there are actually solutions which do not conserve the kinetic energy, okay? So therefore, there are solutions which violate this computation that I told you, which is violated by Scheffer's solution. And actually, he pointed out for the mathematicians a threshold, so a certain amount of regularity at the boundary of which you would know whether a solution might not conserve the energy or should conserve the energy. So above this threshold, all solutions are not chaotic enough to dissipate the kinetic energy. Below this threshold, they're actually sometimes chaotic enough to dissipate the energy. But it's very remarkable because at the time of Onsager, there was no example of any solution whatsoever which is not conserving the energy. So the first example in the mathematical literature comes really in 1993 with the work of Scheffer. Okay, so this number 1/3 is not random. It's deeply related to the theory of turbulence. Okay, so this was hinted actually by Cedric's introduction. So a modest contribution that we have given building upon the work of Nash is that actually you could think about both the Scheffer-Schneeremann theorem and both the chaotic situation in Onsager's conjecture as a kind of generalized Nash-Kuiper phenomenon. So you could think actually that your fluid is doing something which looks like what is happening in the isometric embedding of this torus, which I showed you with a lot of wrinkles. Okay, so that's how it goes. You could actually imagine that you can go from Nash-Kuiper to Onsager conjecture. You are actually wondering what would be the things which are giving you the wrinkles, right? So if you remember, when I go back into the, I think I have time, yeah, 2 minutes. If you go back to the image which I showed you, right, you see this tiny, I mean, first of all, you see pretty big wrinkles, right? So these wrinkles. Then you see other wrinkles, which are these wrinkles over here. And then maybe you are imagining it's actually just the resolution of the beamer, but it's not. So there are tiny wrinkles over there. And then, of course, at that point, the resolution of the beamer stops. And there are also other wrinkles and wrinkles and wrinkles and wrinkles in an infinite series. Okay, so one way you could actually think of explaining these mathematical theorems which I showed you and Onsager's conjecture at the mathematical level is that you could pile up eddies inside eddies in fluids. So vortices inside vortices, and actually produce a very complicated example in which this piling up of infinitely many scales gives you a very irregular solution, which is making this dissipation of kinetic energy. Now, unfortunately, nobody has done numerics on that. So I cannot show you a picture. Well, I can show you a picture, but the picture is kind of fake. So let me tell you why it's fake. So I could show you this picture over here, right? So it looks like, you know, there are a lot of these wrinkles, right? I mean, there are bigger wrinkles, and then inside the bigger wrinkles, there are smaller wrinkles, and so on and so forth. But that's a caveat. If I show you this picture, it's as if I'm really pretending that I'm explaining turbulence in real life. And that I don't know, I'm just a poor mathematician. What I can actually show you is a solution of those equations which are having that behavior. Whether that relates to the real life or not, it's a big question. Okay. Thank you for your attention.